Hello everyone, my name is Radu and I will be presenting our work and our solution to the shared task of fine-tuning a large language model for Ukrainian. The solution was designed together with my colleagues Tiberiu Boros, Stefan Dumitrescu and Octavian Purcaru. For context, the task involved fine-tuning a large language model, evaluated in two different ways. The first evaluation metric was multi-choice question answering. The questions were carefully selected from the Ukrainian External Independent Evaluation, which is a multi-choice question exam. The topics picked for evaluation were history, literature, and language. An interesting and rather important aspect of this challenge was the restriction on the model size. Having to work with models that can fit in at most 16 GB of VRAM without CPU loading to make them more affordable for general users. Also, we are only allowed to use models with open weights, which is a great way to leverage, improve, and encourage the open source community. The second evaluation metric defined was answering open-ended questions. The questions were crafted by Ukrainian native speakers. The evaluation was performed manually, using human annotators and the TrueSkill scoring system. The shared task is pretty relevant for the current landscape because English is the preponderant language in large language model training, with languages such as Ukrainian being severely underrepresented. This results in a performance drop for a majority of non-English tasks. Our solution involved combining multiple techniques from fine-tuning to retrieval augmented generation, and we will see merging. The following diagram illustrates a segmentation of our process in steps depicting experiments as different branches on the path to evaluation. We'll talk in detail about each of those experiments, but before going there, we need to talk about the selection of the base model, which you can see here as a spoiler is Mistral 7B Instruct v0.2. For our selection process, we consider Llama, Llama and Mistral because of their popularity as candidates. Here on the right, we can see the out-of-the-box performance on the benchmark of multi-choice question answering. We move forward with Mistral. It is important to note that all of the experiments, including the previous ones, were performed using the quantized version of the models. Now let's talk about retrieval augmented generation. Well, for our retrieval pipeline we built a raw knowledge base, consisting of the entire Ukrainian Wikipedia and the selection of Ukrainian textbooks. The text from the Ukrainian Wikipedia amounted to almost 3.8 gigabytes. Here on the right we can see some examples of Ukrainian textbooks selected. We also leveraged online textbooks for 11th grade for various subjects. And now we have all of this information and we need to leverage it. The popular way to finding helpful passages for answering a question is through semantic search in the case of RAG. We tried a different approach and used a large language model in the process. Well, the process was actually a multi-step approach, and it involved generating helper queries and extracting n-grams with the large language model. Here on the right we can see the prompt used for generating those queries. By instructing the model to make this type of planning, we are leveraging possible relations between query terms and additional learned information as context for our initial query, enriching it, making it easier to get more relevant n-grams to get more relevant documents for our initial query. This proved to be efficient because it led to an improved accuracy jumping to 40%. The next part was centered around fine-tuning. We curated a set of openly available instruction-based datasets, some of them being translations, to which we added the data provided by the organizers. We used the UE Squad, Ukrainian Stack Exchange, ULPack dataset and some subsets of multilingual datasets, to which we added, as mentioned earlier, the dataset from UNLP. It is important to note that in correlation with the shared task team, we used parameter-efficient fine-tuning so that we keep the hardware requirements as low as possible. We noticed better performance than the out-of-the-box model, but the RAG approach was still better. In literature, it is advised that the fine-tuning dataset to be formatted as instructions, but because we already had a lot of unstructured data, we decided to enhance our initial dataset with fragments from Wikipedia and the textbooks. In the end, we actually saw an improvement. This finding suggests that a good split of structured and unstructured data in fine-tuning is actually beneficial. In the end, we inserted the fine-tune model in the retrieval augmented generation pipeline, obtaining a better score. We also experimented with merging models, because this technique is fairly popular and the merger tends to get better results than the independent models. We used spherical interpolation to combine our model with a top-performing model from the OpenLLM benchmark, which also has Mistral as base. This led us to our final result. We also compared our results on the multi-choice question answering with closed models, and we discovered that our solution beat the ChatGPT 3.5 Turbo out-of-the-box inference. And here we have our results on the open-ended question answering. We can see on the left when GPT-4, which is a big model, is not present, our true scale score is higher than on the right where it is present, but it's still a decent and good score. The model weights are available on Hugging Face, and feel free to download the model and play with the weights and with the things that it can do. Thank you.